Why do we consider indoor air quality important? Because air pollution is a major contributor to the global burden of disease, and airborne viral infections like measles, influenza, human coronavirus, and so on have increased during the past decade. Since humans spend 90% of their time in indoor spaces, the role of ventilation systems becomes essential for us. The air is the invisible killer if we don't pay attention to it. How do we measure air quality? First, we use in vivo experiments, but often we need a lot of ethical permissions and we cannot always obtain them. We also can do in vitro experiments, but they take time and they take money. So nowadays, we are trying to use in silico experiments, meaning we use computational fluid dynamics and optimization algorithms through simulations in order to improve our research quality. The main purpose of our research is to use CFD simulations for inhalation risk assessment in the indoor environment. That means we are trying to study the particles inside a building, inside a room, and how these particles move through the air. We study, first of all, the generation of particles, the transport, the transformation, the deposition, and finally, the infection into the human being. In this way, we're trying to join engineering and medicine. By using engineering, we can think about the building, the mechanical ventilation, and the droplet transport. By thinking of medicine, then we can study also virtual mannequins, the human respiratory tract, and autonomous breathing. By joining all these concepts, then we can apply the concept of digital twins into the indoor air quality research. We have created at first interacting virtual mannequins with physiological functions for our study. We have created a speaking model and we have applied it to an infected person. We have also created a potential host with a respiratory tract attached to this person. The respiratory tract we have created goes from the nasal cavity, the larynx, the trachea to the bronchial region. And we have also introduced a breathing model to this person. We have used a lot of computational models in order for this person to be constantly breathing and the infected person to be constantly speaking. Finally, in order to analyze the indoor environment, we have introduced this interacting speaking person and interacting breathing person into a building. We have created a lot of air patterns in the building. We have applied concepts such as mixing ventilation, displacement, underfloor air, impinging jet, and stratum ventilation. And we have moved the air in this room in different ways to see which one of our optimized ventilation systems is the best option for us to live in. In order to do this, we have performed different simulations using Fugaku. So each simulation requires 600 nodes, and the execution time of each simulation is 72 hours. Meaning that we need almost 45,000 nodes hours per simulation. In a computer, this is absolutely impossible to perform, so that is why we need HPC in this type of analysis. Finally, we have analyzed the impact of indoor airflow on particle movement and deposition, meaning that we have actually studied how these particles go into the room from the infected person, how these particles move through the air from one person to the other, and how the potential host can inhale these particles, how many particles can they inhale, and where these particles are deposited in human tissue. By doing this, we can actually calculate the exact site of deposition of the particles and how this site, the size of the particles, and the number of said particles affect the human health. By doing this, we can analyze which of the ventilation systems we have proposed is the best option. In our simulations and in our studies, we have concluded that the best ventilation type is displacement ventilation because the particles are displaced to the upper region of a building. In this manner, we don't have to inhale the particles, but the particles go above the breathing zone without having an impact on human health. Finally, we have optimized this type of ventilation system. But why have we optimized this ventilation? Because when we talk about a ventilation system, before optimization, we have to think on either infection risk or energy consumption. But these two are not always in balance. By using optimization and generic algorithms, for example, we can bring the infection risk and the energy consumption of the building to the same level. In this way, we can ensure that the building is sustainable either in human health and also in the money spent to sustain this ventilation system. As a proof of concept, we have first designed a very simple room, and in this room we have put a digital twin that is constantly speaking. We have analyzed two objective functions. One of them is the infection risk. How can we improve the infection risk? How can we minimize the infection risk in a building? And our second objective function is the energy consumption in terms of how to minimize the energy spent in a building in order to minimize the cost of the building. In this type of simulations, we have also used HPC and we have also used Fugaku, because each simulation requires 46 nodes and the execution time of each simulation is 48 hours, meaning that we would need approximately 3,000 nodes per hour per simulation. This is also impossible to do in a normal computer, but using Fugaku, we can overcome this problem and we can create as many simulations as we need to improve the indoor air quality. By introducing our two objective functions, we can apply this into two ways. We can, number one, reduce the power consumed in a building, and we can also reduce the viral density that is in a building. Let's think of two simple scenarios. One scenario is where there is no optimization and the inlets of the air, the outlets of the ventilation system, the sides of these inlets and outlets are randomly put together. In this time, there is no optimization, so the outcome of this type of ventilation system might not always be the best, which is to what point one is referring in the presentation right now. But if we apply optimization, then we can analyze different parameters, for example, the size of the outlet, the size of the inlet, the location of these parameters, and then we can actually introduce optimization into this building, meaning that we can choose the exact size and the exact location of where the performance of this ventilation system is the best. So in this case, from P1, where particles stay in the breathing zone and are a detriment to human health, we have case 2 in P2, where the particles can be airborne to the upper region of the room, meaning that they do not represent a big impact on human health. So with our simulation, we can create different types of analysis in the indoor environment. We have developed interacting virtual mannequins as digital twins to join in the ventilation studies, so we can create a sustainable indoor environment. And we have carried out comprehensive evaluation of several ventilation systems to choose which one is the best for human health. And from there, we have optimized this best ventilation system in order to further decrease the infection risk and to further improve the energy consumption in a building. But we cannot do that without applying HPC and without using Fugaku, because the simulations that need to be carried out for actually calculating the trajectory and the path of particles is very important when we're trying to calculate human health. Thank you very much.